Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of Petro, Arab Oil and Gas Academy, Arab Garo, SPE Egypt section, I'd like to welcome you all for our long-awaited Q&A session for the well-renowned Dr. Moustafa Oraby. I'm Mayar Tariq, a third-year gas and petrochemical engineer student at Alexandria University, and I'll be your moderator for today's session. Before we start, please, I'd like to remind you to drop your questions in the Q&A section below and to keep the chat box professional and ethical. Now, without further ado, let us give a warm welcome to the well-renowned and distinctive Dr. Moustafa Oraby, who will answer all your questions during today's session. Dr. Moustafa Oraby has a 25 years experience in the petroleum industry. He holds a PhD degree from the North Carolina State University, the United States, and a master and bachelor degrees from Alexandria University. Dr. Oraby joined Alexandria University in his early career as an assistant lecturer till he obtained his master's degree. He also used to teach at community colleges in the United States. In industry, Dr. Oraby held many positions in all aspects of petroleum industry and lived in many countries around the globe. Thank you so much, Dr. Mustafa, for coming today. It's our pleasure, and the mic is yours.
Thank you, Mayar, for the nice introduction. Guys, as Mayar just mentioned, this is a Q&A session. This is the second one. We did one about probably 3 weeks ago or so. So this is the second group of questions regarding the reservoir characterization, unconventional reservoir, and also saw some questions from wood logging as well. And also saw some questions you just posted a few minutes ago. I'll try to cover those as well. Okay. So without any further ado, let me start with that session. Here are some of the questions. I'm gonna, list all of them for the time being, just to go through them, all of them. Then we'll try to answer most of them as we go through. I also grouped them to groups where some of the questions actually they repeat or they are linked together. So I grouped them to about 4 or 5 groups, trying to take every group in a different direction. Okay. So some of them were talking about the organic matter and dolostone. This question actually repeated several times because in dolomite you can sometimes see uranium readings on the spectral gamma ray. And also we said that in the unconventional reservoir you see also uranium reading on a spectral gamma ray. So the question is which is which? How can I differentiate? This is a very good question. I'll go through this. I'll go through this in some details. So guys, bear with me and make sure you understand all the way how we can differentiate and distinguish, because this is a critical question. Then at the same time, we're talking about, for example, I would like to know how I could master the reservoir. What are the books I can read? I'll talk about this also later. Can you suggest some of the books? I will also talk about that later. What's the difference between cementing and tubing? That was a question I didn't really understand. That you mean cementing? You mean the casing and tubing? Is that what you mean? I'm not really sure. There's also one about the LWD. How can we use the LWD to evaluate wells? Talk about this in a little bit of some details. For the ZIFT tool, how does current go through the matrix? It can go easily through the mud. That was actually fully explained in the webinar of the well logging, but I will go through this one more time to make sure that you guys understand it. Also the induction log, why we see differences between the phase and the amplitude. I will touch base on this. That goes back to what we call geosteering and bit boundaries. I will try to explain this in a little bit of some details. The question that I really insisted on, I don't want to see this question anymore, which is, can a source rock be a clay? Please refrain from asking this question again. Guys, from now on, clay is not, will not, and cannot be a reservoir. Period. Clay is not, will not, and cannot be a reservoir. Okay? I will answer that question again. And please don't ever think that the clay will be a reservoir anyway. Okay? Not because the source rock has high gamma ray, that does not mean it's clay. And if you actually watch the unconventional reservoir, I repeated this several times. So please don't ask that question anymore. Clay is never, will never, and cannot be a reservoir. Okay. Then we'll continue on the characterization is the density drawn by the scale of PU. Again, I discussed that in the wild line. I will repeat it again today just to make sure there is no confusion. How can differentiate between clay zone, dole stone? I will talk about that, as I said. Regarding the lecture characterization, what is the difference between cap rock and seal rock? That question is really a very repeated question. Guys, there is no really difference between cap rock and seal rock, but the rock itself can be a cap rock if the permeability is very low. And if we call it cap rock because the cap rock has a very high capillary entry pressure. If you have a very high capillary entry pressure, this means that your permeability is very low. And that's why if the permeability is very low, that actually stops any hydrocarbon from further migration. So that's why we call it cap rock. So any rock that stops the hydrocarbon from going further, either being part of the rock itself or another type of rock like salt, for example, salt dome. Salt dome is also a cap rock. So it's the both, they do the same function, but one of them just is characterized by a very high entry cap pressure. That's why you call it a cap rock. Okay. So let's just go for start with the group by group and go in some details of some of these questions. Okay. So group one is these two questions or three questions, which is the organic matter and dolostone. Organic matter and dolostone and the density on the porosity log. I will go through these three questions in the first. Okay. So let me start with lithology. Lithology and how can we differentiate between dolomite and anything that has high uranium component. Okay. So guys, the whole thing now is if I have high uranium, we all agreed in the unconventional reservoir, it is a source rock. Okay. But the source rock also have the source rocks have other characteristics. Being laminated is a condition. You may not see that in a dolomite. Having a very, very high resistivity, you may not see that in a dolomite. Having very low porosity, you may not see that in a dolomite. Okay, and dolomite can also be a source rock. Okay, so dolomite itself can also be a source rock. We all agreed the source rock is not clay. It's a normal reservoir, normal clastics and carbonates. The only difference is that its grain component is very, very, very fine to the limit of being the same size of the clays. That's why we call it shape. Okay? So let me start with this. How can we identify lithology? We looked at the gamma ray neutron density in the well logging and the characterization webinars, and we actually put this example together. We looked at a sequence of rocks. We have clay, we have sand, we have lime, and we have dolomite as layers. And we, for the simplicity, we put that all of them have about 20 PU. So it's 20 PU sandstone, 20 PU limestone, and 20 PU dolomite. Okay, topped by a clay. So the clay is on the top and followed by these three reservoirs, sandstone, limestone, and dolomite. We started looking at what is the behavior of the gamma ray neutron and density in front of these rocks. And we said that the behavior of the neutron and the density combined with the behavior of the gamma ray will tell us the lithology due to the separation between the neutron and the density. We said that the API asked all of us to put the logs on single common scale, which we all go for limestone scale as a representation of the logs that come from the service company. So in this case, it's easy in all of us. When we standardize the scale, it's easy for all of us to put some standards and also some understanding of how the behavior between the neutron and the density, okay? So in this case, it's very important to look at the behavior of the neutron and the density in this type of sequence. Now, if we look at one by one, let's just go for the gamma ray. Gamma ray will read high in front of the clay. Since we all know that this is a reservoir, we expect that in front of the reservoir, we have low gamma ray. We'll come back to when the dolomite have a high gamma ray, because sometimes dolomite will have high gamma rays, okay? So let's just go for the first thing, which is gamma ray is high only in front of the clay. and it's clean in the reservoir. So this is the standard thing. Sometimes, as I said, dolomite will show some high activity of the gamma ray. Now, how can we differentiate this? That I will cover this after I review the behavior of the neutron and the density on the limestone scale. So first of all, here is the gamma ray in front of the clay reading high, and the gamma ray in front of the reservoir reading low. Now, if I take this and I go to the neutron, I say, neutron tool, how will you respond to these type of sequences? Now, I have three scales: limestone, sandstone, and dolomite. We all agreed as by API standardization is we need to put all the logs on limestone scale. So even if it is sandstone, we have to put it on limestone scale to standardize the scale. Okay. So now 20 PU is here, and as a sandstone, how will it look on the limestone scale? Then you go down on the limestone scale and you read the porosity. So you go to the 20 PU of the sand, you go down on the limestone scale to read what is the porosity of the 20 PU sandstone will appear on the limestone scale. You will see it's about 16.5 or 17 or whatever. So this means the porosity will decrease. It will appear as, make sure you understand this wording, it will appear as 17 PU because it's on the wrong scale, okay? Because it's sand put on a limestone scale. So sand put on a limestone scale, the porosity will decrease, okay? Now, limestone itself is 20 PU. So limestone is not gonna change because it's limestone on limestone, okay? Limestone rock on limestone scale. There is no reason to change. So it will be at 20 PU. Now, if you go for the 20 PU dolomite, all right? 20 PU dolomite is here. I go back, I go there, and I see how much how will it look on the scale of the limestone. So I'll go up with the arrow and I read the porosity there. The porosity will be about 27.5 or so, oh yeah, 27.5 or so. So looking at this, the porosity will be lower than the truth if the rock is sandstone. It will be higher than the truth if the rock is dolomite. Keep this in your mind. It will be exactly the same if the rock is limestone. Why? It's limestone rock on limestone scale. Now, if I have sandstone rock on limestone scale, my porosity will appear less. And I'm also stressing on the word appear. My porosity will appear less on the limestone scale. Okay, if I go for the dolomite, my porosity will appear higher on the limestone scale. Everybody agrees on this, right? Okay. Now we go there and say, okay, now I know in front of the sand, my porosity is reading less, 16.5. In front of the lime, it's reading exactly 20. In front of the dolomite is increasing and reading 27.5. So this how my log will appear on the limestone scale. By the standardization of the API, everything has to be on the limestone scale. Okay, we raised that question before in the other webinars, why we are doing this, and said because this actually will make things easy later when we try to calculate the porosity and the lithology. Now, what is the porosity in front of the clay? We all know that the neutron tool responds to hydrogen. The neutron tool does not actually measure porosity, it measures hydrogen. And since hydrogen lives in the pores, that's why we relate what the neutron tool reads to the hydrogen component, okay? Now, to understand how the neutron will react in front of the clay, we need to go and look at the clay structure. If we look at the clay structure, it contains a lot of hydrogen. Here is hydrogen here, 8 hydrogen in the L-light. We see 4 hydrogen here in the smectite plus 8 hydrogen here, so about 12 hydrogen in the smectite. So all these clay minerals, they have lots of hydrogen. If the clay mineral has hydrogen, it will show higher porosity on the neutron tool. That's why I can see high porosity in the neutron tool in front of clay. You don't memorize anything, everything, and as we understand how the tool works, it's easy to predict the response of the tool. So now we understood how the neutron tool will react in that sequence of rocks. Okay. Now, If we look at the density of all of these rocks, here is the density tool. To take the density tool, you measure density, then you transform density to porosity. Okay, so here is the density porosity, which is raw bulk. We measure raw bulk, raw matrix divided by raw fluid minus raw matrix. Why am I putting this equation? Because we agree that everything has to be on limestone scale. Keep this in your mind. Everything has to be on limestone scale. Since I will put the neutron and the density on the same track, then I have to use the matrix as limestone matrix. Okay, so this raw matrix here has to be limestone matrix. Since this is a limestone matrix, I know the density of limestone. Density of limestone is 2.71. So this equation should not be left this way because raw matrix now is known. I have to use the limestone as per the API standards. Okay, so that's why this has to be 2.71. So everybody understand that? Since we standardize as per the API requisition, we have to have everything on limestone scale. So my equation is not going to be absolutely unknown this way. It will be 2.71. Okay, why the raw fluid is 1? Because every company, they should calibrate their tool. When the companies calibrate their tool, they calibrate it on a tank of 100% water. So that's why the raw fluid in the calibration, where the tool is calibrated on, is actually 100% tank of water. So that's why the raw fluid has to be kept 1 because of the calibration of the tool. So once I read from my tool the density, then this density will be converted to porosity. Okay, so the density will be converted to porosity. Okay, all right. So now here is the density of the 20% PU sandstone. Here is the density 2.32. Here is the density 2.368. Here is the density 2.46 and 496. I use the equation to transform the density to porosity. If I do this transformation, then I get that the density, the density porosity of the sand is 22.2. Remember, the porosity was reading low on the limestone scale, but the density porosity is reading high. So the neutron porosity reads low and the density porosity reads high. Okay, on the limestone scale it will be the same because limestone on limestone. For the dolomite, we will find that the density porosity is reading low. So the neutron porosity was reading high, but the density porosity is reading low. So you will see that the behavior of the density is opposite to the behavior of the neutron. So if the neutron is reading low, okay, on front of the sand, the density porosity is reading high. If the neutron is reading high in front of the dolomite, the density porosity is reading low. Look at this. The increase of the neutron, the increase of the density here and the decrease of the neutron is the same. So they cancel out. Now, if I added these two together and I divided by 2, I took the average, I will come exactly to the right porosity. So that's why you don't worry about putting all of them on a limestone scale. It doesn't matter. Because if you take the average of the neutron porosity and the density porosity, add them up. If you add these two, it's actually 40. Okay. If you divide the 40 by 2, gives about 19.5, 19.6 or whatever. It's very close to the actual porosity. Here is 20 PU and here is 20 PU. Okay. So the separation here shows certain type of characterization. So if the density is on the left and if the neutron is on the right, then this is sandstone. If the neutron and the density are overlaying, this is limestone. If the neutron and the density are separated, where the neutron now is on the left and the density is on the right, it's a dolomite. That's why if you go to a work in any company, when you look at the logs, you look at the behavior of the neutron density. From the behavior of the neutron density, and since we are following the API standards, I can easily identify where is my sand zone, where is my lime zone, where is my dolomite zone, by just looking at how the neutron and density are separated. So for any neutron density log, guys, from now on, look at the behavior of the neutron and the density. If the density is the one on the left and the neutron is the one on the right, you actually swear that this is a sandstone. If they are overlaying, you can swear this is limestone. If they are separating opposite to the sand, it means that the neutron is on the left, the density on the right, that's a dolomite. Okay, all right? So we all agree on this. We need to go back to the clay, how the clay will look like on the density. You go back and look at the clay one more time. Our clays, they have very interesting things. They have aluminum, they have iron, they have magnesium. All of these are metallic components and they are heavy. That's why the density of the clays are a little bit heavy. That's why if it is heavy, it will be on that side. So the density will be on that side because the density of the clays are heavy because of the metallic components of the clays. So I now understand exactly how the neutron and the density will react. So if I see the separation between the neutron and the density, that the neutron is left and the density is right, that's a dolomite signature or it's a clay signature. How can I differentiate? Clay normally have high gamma ray. Dolomite has low gamma ray if they are a reservoir that does not have uranium in it. So the question that came from you guys, what if I have uranium in there? Okay. What if there is a uranium in the dolomite, which we call it the dolostone? So you have the dolostone, which have the uranium in the dolomite. What can I do? So that's your question. Okay. All right. So now if I assume that my uranium now is reading higher gamma ray. So that's the question that I'm going to answer now. I just reviewed what we understood from the normal behavior. This is abnormal. The dolomite is having uranium. This is something abnormal, but it happens in many reservoirs. So I can see higher gamma ray in the dolomite. Okay. How can I differentiate that? To answer this, actually, there are two methods of doing this. Okay, just pay attention to this. There are two methods of doing this. One of them, I call it a cheap one. You don't actually pay money for this. You can get this quickly. Okay. The second one you need to pay money for. It's more expensive one. So there are two methods of identifying the dolostone. Or if I see higher gamma ray due to uranium, okay, how can I say this is a dolomite or not? Okay. So a cheap one and an expensive one. Expensive one means you run another tool. But now I have only the triple combo. I have gamma ray, neutron density, and resistivity. Okay, I don't have any extra tools. How can I differentiate if I don't have any extra tools? That goes back to the definition of the litho density tool. The tools, guys, now, the density tool is called litho density. Litho means it actually can identify lithology by itself. So the density tool gives you two measurements, not only one. Okay, the density tool gives you two measurements, not only one. The first one relates to lithology, which we call it PE or photoelectric. Okay, the second one is density. So we have two measurements, density and photoelectric. Density we understand. Then what is the photoelectric? Okay, so pay attention to this because this is a very important thing. So the density tool gives you two measurements, not only one. Give you one that's called density, which we normally use. There is another one called PE, or sometimes they call it PEF, photoelectric factor. PEF or PE photoelectric is a measurement that actually relates to lithology. So there is a measurement that comes out of the density tool that relates to lithology. Why people don't talk much about this measurement? Because this measurement is very shallow. Okay, so if you have a very bad borehole, it means you have a lot of washout. Your borehole is irregular because the driller didn't take much of care when he drilled the well, so the borehole is not in a good shape. This, the photoelectric or the lithology part of the density is very shallow. It can be highly affected by the mud. Can be highly affected by the mud. So I will explain it now. But pay attention, be very careful when you use the photoelectric. It's a very shallow measurement. It's about 1 inch depth of investigation. It means it can be heavily affected by the mud or the drilling fluids. Okay. So when you use again, I'm repeating myself again.
when you use the photoelectric, which we will talk about it in some details now, be careful because it is a shallow measurement and it can be affected by mud. If it is a shallow measurement and is affected by mud, in your case, go ahead and use the expensive solution. So if the cheap solution didn't work, you have to go and use the expensive solution. Okay. So let me go for the cheap solution first. So the litho density tool actually provides two measurements, lithology and density. That's what we agreed on. For the density, we understand that. What does it do? You actually have a gamma ray source and you have gamma ray detector. The gamma ray source emits gamma ray with a certain energy. The gamma ray interacts with the electrons and you get the density out of this measurement. We actually discussed this in the formation evaluation webinar. So, go and review that one if you still didn't watch this webinar, okay? So we use a gamma ray source. From the gamma ray source interaction with the electrons of the formation, I can predict the density, okay? Predict the density on what basis? Actually, any density in any gamma ray will have one of three types of interaction with the electrons. Pay attention to what I'm saying here. You have one of three types of interaction with the electrons. Three types of interaction. The first one, we call it Compton scattering. Okay, we have Compton scattering. Second one, we call it photoelectric. Okay, third one, we call it pair production. So there is one probability that it will make Compton, or it will go through photoelectric, or it will go through pair production. Then the question is supposed to come, when each one of these will occur, when the gamma ray will do Compton, when the gamma ray will do photoelectric, when the gamma ray will do pair production. This is controlled, guys, by the energy of the gamma ray. Okay, so the energy of the gamma ray will decide which one of these interactions will happen. So this means that the Compton interaction will happen at a certain energy, photoelectric will happen at a different energy, pair production will happen at a different energy. Okay, so that interaction, the probability of these interactions will rely on how much is the gamma ray energy. Okay, we need to stress on the pair production. We don't like pair production to happen. We don't like pair production to. What is the pair production? Pair production means, from the word pair means two. Actually, what will happen is the gamma ray will disappear in the formation. It will get absorbed and two electrons will come out. Okay, let's just understand. That's why we call it pair production. It produces pair of electrons. That's what a pair production means. It produces a pair of electrons. So two electrons will come out of the gamma ray and the gamma ray will disappear. Okay. Okay. What is the condition for this? The condition for this, that your gamma ray has to be above 1.02 mega electron volt. Okay, 1.02. What is the magic number? We will understand the magic number in a second. What is the 1.02 mega electron volt? Why the pair production requires 1.02 mega electron volt? We'll understand this in a second. But you now know the condition for the gamma ray to make an interaction called pair production, where the gamma ray disappears, it doesn't come back to you. You will not be able to count it, but two electrons will come out. That's why, since I will not be able to count the gamma ray, it's not going to come back to me. It's actually very confusing to me. I send the gamma ray, I don't receive it. I like to send the gamma ray and receive it back, and I can find out how much energy it lost, so I can find the energy and the density. Now, the gamma ray is disappearing. So that's confusing to me. That's why we never allow the pair production to happen in our density tool. Okay, we are not allowing the pair production to happen. Then you can ask yourself a question. How can I control this? Simply, your gamma ray source in the density has to have energy below 1.02 mega electron volt. If my source of gamma ray that I use in my density tool has energy less than 1.02, I'm sure that pair production will never happen, because pair production requires energy above 1.02. Okay, if the energy is below 1.02 mega electron volt, pair production will never happen. Okay, so I can prevent the pair production from happening, right? So the pair production, if my gamma ray source is less than 1.02, then I'm in a safe zone. Pair production will never happen, and I'm left with two of them, the Compton and the photoelectric. That's why if you go for the any density tool, the density tool uses energy less than the 1.02. The question now, what is the 1.02? Okay, we actually said pair production. Pair production of what? Pair production of electrons. So the gamma ray will disappear and the electron will come out. Then what is the energy of the electron? You know, Mr. Einstein said energy and mass are correlated. Okay, I'm sorry, I'm going deeper. I didn't actually cover this before, but since you are actually asking questions, you have to get deeper into this. Energy equals mc squared. We know the mass of the electron. We studied this even in probably in middle school and high school. The mass of the electron is 1.69, 1.6 10 to the power 19, negative 19. So you know the mass. You know the c. C is the speed of light. If you do the multiplication, mc squared is equivalent to 0.51 mega electron volt. So the electron is equivalent to 0.51. But this interaction makes how many electrons? 2. So you multiply 0.51 by 2, it gets you the 1.02. So the 1.02 is not a magic number. It's actually equivalent to the mass energy of a rest mass in electrons. So the electron by itself, if you convert its mass to energy, okay, then it's 0.51. And since they are pair, you multiply this by 2, then you get 1.02. So 1.02 is the threshold to produce two electrons, okay? Now, to prevent, as I said, to prevent this from happening, use a source. That source has to have less than 1.02. And that's why our source in the density is the cesium-137. Cesium-137 gamma ray source that we all use in the density tool has an energy of 0.6 mega electron volt. 0.6 is less than 1.02. So with using this source, that's why sometimes we specify the source for certain reasons. So the source is cesium-137 because its energy is less than 1.02 mega electron volt, and that prevents the pair production from happening. Okay, all right. So now we are left with two of them, Compton and photoelectric. Compton, we use it for density, and Compton means the gamma ray goes, interact with the electrons and loses some energy and come back to the detector. Okay, so that's what the Compton is. So Compton gamma ray does not disappear. Gamma ray loses some energy to the electrons and come back to the detector with a lower energy. From the energy that the gamma ray is coming back with, I can predict what the density is. So Compton is a function of density. Right? So what is the photoelectric? Photoelectric is the function of lithology. Is a function of lithology. I will put the photoelectric here. This is the probability of photoelectric. It's called Z equivalent. What is the Z equivalent? Is the atomic structure of a component. So the photoelectric depends on the atomic structure of the rock. Since we have three different types of rocks. One of them is the sandstone and the limestone and the dolomite. Z equivalent is a complicated calculation. I don't want you even to go through it, okay? Unless you study chemistry and stuff. So Z equivalent is actually an equation that you use because why you call it Z equivalent? Because, for example, in the sandstone, you have silicon dioxide. So you have silicon that has electrons, and you have oxygen that has electrons, and they combine together to make silicon dioxide. That's why they have something called Z equivalent, equivalent to this combination. Okay, so silicon dioxide will have a Z equivalent. Limestone, which is calcium carbonate, will have a Z equivalent. Dolomite, which is the calcium carbonate plus magnesium carbonate, which is also has its own Z equivalent. If you do and calculate Z equivalent, Here is the Z equivalent for all the components. Okay. All right. So Z equivalent for silicon dioxide is 11.78. Z equivalent for calcium carbonate is 15.71. Z equivalent of dolomite is 13.74. Take this number, divide them by 10, take the power to 3.6, gives you what the photoelectric is. So the photoelectric is the probability of getting lithology information due to the Z equivalent, because the Z equivalent of sandstone is different from limestone, is different from dolomite. Here is the Z equivalent after applying the Z equivalent equation. As I told you guys, I'm not going to put the Z equivalent equation here in front of you. I don't want to make it difficult on you. But if you like to see it, it's in the books. I will refer you to some books actually to look at the Z equivalent. Okay, so the Z equivalent calculation for silicon dioxide is 11.78. For calcium carbonate is 15.71, and for dolomite is 13.74. If you take the Z equivalent divided by 10, you get the PE to the power 3.6. Here is the PE. Now, if you take the Z equivalent divided by 10, go to the power 3.6, so the PE is 1.8 for sandstone. So this means if the density tool or the litho density tool, if I look at the PE curve, which is the photoelectric, and I see the PE is reading 2, I know it's sandstone. If the PE is reading 5, I know it's limestone. If the PE is reading 3, I know it's dolomite. So the PE will tell me where is the dolomite. So in case you have a high gamma ray, okay, and the separation of the neutron is showing dolomite, and the high gamma ray is because of uranium, then you will see that the PE is reading 3. So to confirm that this is a dolomite or not, go and look at the PE. If your PE is good enough, as I said, PE is a shallow measurement. It may be affected by the shape of the well bores, which is the washout. It may be affected by the washout. If you're sure that your hole is in a good shape and the density is reading good density and good PE, then you use the PE. In this case, in front of the high gamma ray, you will see PE is reading 3, indicating dolomite. If the PE reads 5, it's a limestone. If the PE reads 2, it's a sandstone. So 2 for sand, 3 for dolomite, 5 for limestone. Okay, so that's a cheap way, easy way to find or identify your dolomite. If you are not identifying this with the dolomite because of the bad borehole condition and your PE is not in a good shape, then you have to go for the expensive one. Expensive one, you need to run the spectral gamma ray. You have no other option. Okay, look at the spectral gamma ray and confirm that this zone is showing separation of clay, because the separation of dolomite is the same as separation of clay. And make sure that the high gamma ray is not because of the clay. It's only because of the uranium. Okay, so you run the spectral gamma ray that identifies potassium, thorium, and uranium. And we all know clays don't have uranium. Clays, they have potassium and thorium. Okay, so the potassium and thorium will be high in front of clays. Uranium will be high in front, either a normal dolomite reservoir or in unconventional reservoir or in unconventional dolomite reservoir, because dolomite, as I said, can be an unconventional reservoir, okay? Can be a source rock. Okay, so this actually depends on the energy, because the energy of the 3 of them are different. That's how this tool identifies the 3 components. Now here is an example. Here is the total gamma ray. I have no clue which is which. When you run the spectral gamma ray, here is potassium. You can see potassium is reading high on the top, reading low all the way here, and it's reading high at the bottom. Then I put the thorium close to it. I can see thorium is reading high, thorium is reading high. When the potassium reads high and the thorium reads high, that's a confirmation of clay. Everybody understand that? To say that this zone is clay, you have to make sure that your potassium is reading and your thorium is reading, both of them. Okay, so potassium is reading and thorium is reading. Potassium is reading and thorium is reading. That's a confirmation of clay. Here, I don't see any reading of potassium. It's very, very low. No reading of thorium, very, very low. But the gamma ray is reading very high because of the uranium. So this zone is a clay and this zone is a clay. But this zone is not a clay, cannot be a clay, despite it has very high gamma ray. So what is it? Where this gamma ray is coming from? It's coming from uranium. So now I know this is not clay, it's uranium. And because it is uranium and I see the separation, I can say this is a dolomite zone. So I can identify the dolomite zone under the condition that my potassium and my thorium are very low, and the one that's reading high is my uranium. Okay, this is an expensive one because you need to run the spectral gamma ray. If you don't have the spectral gamma ray, go to the PE, and if the PE works, that's good. If it doesn't, then in the next well, or probably in cased hole, because you can run the spectral gamma ray in cased hole as well. So you can run it in cased hole and find out if it's uranium. I'm sorry, if it is uranium or not. And by the way, you can also get this from cuttings. There are so many ways that you can identify lithology. You can do that also from cutting while drilling, so you can identify the lithology there. So that's the first question: how we can identify the reservoir if it is dolomite. There are two solutions: either using a PE or using the spectral gamma ray. Okay? All right. Is density log drawn by the scale PU or density? Guys, again, since we put the neutron and the density on the same track, they have to be consistent. You cannot put two logs on the same track with two different scales. That's confusing. Okay, so that's why the API said, guys, you put both on the same track, because you measure porosity from the neutron, and you can calculate density from the density. I'm sorry, calculate porosity from the density. So you measure porosity from the neutron, you calculate porosity from the density. That's why they can be consistent on the same track. When you do that, general rule, you have to be consistent. If you combine two logs in one track, you must be consistent. And that's why the scale of the density is a density scale, yes, but it corresponds to the neutron porosity scale. Everybody understand that? The limits of the density is you have no choice on. You are forced to use this limit. If I am free to use any limit, why I'm putting 1.95, 2.95? I can put them 2 to 3, 3 to 4, 1 to 5. Are you free to do this? No, you're not. You are forced to use 1.95 to 2.95. Why? To be consistent with the scale of the neutron, because they are both on the same track. So yes, you're putting your density limits as a density, but these density are forced on you. You have no choice on it. Forced by what? Forced by the porosity of the neutron. Okay, that's why they are linked together. Let me go back and look at this in some more details. Neutron porosity all on limestone scale. Okay, density on the same track has to be also on limestone scale for consistency. That's why we have to use 2.71 as raw method. It is our density equation, 2.71. We also talked about the raw fluid. We said it's a calibration tank, and that's why the raw fluid has to be 1. So my equation is 2.71 and the fluid is 1. Now, if I go there and I say, well, what is the maximum porosity of any rock? Maximum porosity of any rock is 47%. For simplicity, we'll make it 45. Okay, so that's why the first porosity on the neutron is 45. The neutron starts from 45 to negative 15. So the 45 is coming from where? Because your maximum porosity is 47. Instead of putting 47.6, make it 45. If I take the 45 now, and I go to the density equation, I put the equation at the porosity as 45. Then I have to choose that to be consistent with the 45. So the 1.95 that you chose is not out of your choice. It's out of this equation. Then if you do the math here, raw bulk is 1.95. So the 1.95 is no choice. You cannot change it. It's corresponding to the 45. So that's why we always say density scale is consistent with the porosity scale. All right. So the limits are consistent. So either you read the density as density or you read the density as porosity. It doesn't matter because they are consistent. So you can read the density as density and also you can read it as porosity because that's a confirmation. That's what you did from the transformation. Okay. So that's why you see here 0.45 and 1.95. The 1.95 is not a magic number. It's a calculated number. Okay. Calculated from where? From being consistent with the 45. So this one is consistent with this. So you have no choice on that. Similarly, this one is consistent with that. Let's go back and use the equation. 2.95 for simplicity. I'll take the 2.95 and I put it here. What is the porosity if I use the 2.95? It's negative 15. So that's why the negative 15 is there because I have to go to 2.95. Okay. So 1.95 to 2.95. Density here is 45. Density here is negative 15. So the density has you have no choice. It's not really a freedom of density scale. No, you are forced to use this density scale to be consistent with the porosity scale. I hope this is clear for everybody's mind now. In the scale of the neutron density track, you can read the density as density if you want. And you can read it as porosity as well, because the density scale and the porosity scale are not haphazard. They are calculated scales based on consistency on limestone. I hope I am clear on this, okay? All right. Okay. Now we go to group 2, which is said induction and induction to well logging. Can we use LWD to evaluate vertical wells? Or are there some factors or this take it one by one? Yes, you can. You can use LWD for sure in vertical wells. We don't do that because, okay, we don't do that normally because we actually use LWD in highly deviated well and horizontal wells because it's difficult to go with the wireline. Why people prefer wireline over LWD? Guys, LWD, it needs some skills that you may not be having now. Okay, so LWD is different from wireline. For example, at the time you log wireline, there is no drilling. Things are very quiet. There is no mud movement, no circulation. There is no motors in the hole. There is no bits, or there are no bits in the hole. Okay, so things are very quiet. So, and this was the first thing that they did in the measurements. It was wireline measurement. So people are raised on how to get experiences on wireline data. So if there is a possibility of having wireline data, we do the wireline data. That doesn't mean we don't use the LWD. Now, no, we use the LWD, but make sure that the LWD has an environment where you have motors in the hole. So there is vibration in the data. You have circulation in the hole. So there's actually changes in the data. Actually, the motor rotates. This means that the tool is rotating. So it's not seeing one side of the hole. It reads the 360 degrees. Unless you keep this in your mind and you are a very well-trained engineer on LWD, you will find difficulties to do the LWD. So that doesn't mean we don't use it. No, we use it. I personally use an LWD all the time. But you have to have your own experiences and you have to make sure you understand the environment. The wire line is not rotating. The LWD is rotating. Wire line, there's no much circulation. LWD, there is much circulation. Wire line sees only one side of the hole. LWD 360 of the hole. No vibration in wire line. There are vibration in LWD. Unless you know that and you know how to deal with it, don't use the LWD. Okay. So yes, we do use LWD under the circumstance, under the condition that we are experienced in LWD. So yes, you can, but it will reduce your cost if you do that. But be careful because it requires lots of skills. Okay, to do the LWD, it requires skills, but we do use that. Okay, we do use the LWD. Right, harder than the wireline. Now, is it important to center caliper during the evaluation job, guys? We always use centralizations or centralizers. Yes, we do. We centralize. Here is an example of the tool string in wildlife. Look at this. There is a centralizer here. There is a centralizer there. We use more than one centralizer, guys. Depends which tool. Okay. If you need to centralize a tool, go for the service company. Say centralize this tool. They put a centralizer. They will make sure the tool will be centralized. Okay. So yes, we do centralization. Yes, we have centralizers. And if you look at any sequence of tools put together, we call them the stack. So the tool is stack here. If you look at this, we actually use centralizers everywhere. Here is a centralizer, here is a centralizer. Some of the tools also, we use the knuckle joints. I'm not sure if you guys know that stuff or not, the knuckle joints. If I need to make sure that the tool actually is very much attached to the wall, we use what we call knuckle joint to make sure that the tool is actually attached to the wall, like the neutron tool and the density tool. They need to be attached to the wall, not centralized. Use a knuckle joint to do that. So we can actually change between centralized or not. We're using knuckle joints and we're using centralized. Okay. So yeah, we can do that, and we do that all the time. For resistivity tool, how does current go through the matrix? It's not easier to go back through the mud. I actually explained this more than once in the logging and the characterization. But let me repeat this one more time. We focus the current. Focusing current means not allowing the current to go through the mud. That's what focusing is. Okay, that's why we call focused resistivity. Okay, how can we do that? We don't allow the leakage. Here is your well bore. Here is your current source, and here is your focusing. How can we do the focusing? Here is your receiver. Actually, what we do, we put what we call a current guard. Here is a guard, and here is a guard. These two guards does not allow the current to escape or leak. Okay, so the guard is actually two magnetic fields that forces the current to go through the formation. That's why we call it focused current. Okay, so we are not allowing the current to go to the easiest or the easier path, which is the mud. Okay, your point is very well taken, but that's already discussed before. We focus the current by using two focusing guards. The two focusing guards forces the current to go into the formation, not in the mud. Okay, so we take care of this by focusing the current. That's why we call it focused resistivity. Right? For induction tool, when we translate phase shift or attenuation or amplitude into resistivity, are they equal? Not, no, they are not. Okay, because they are equal in one case. If there is no bed boundaries, you know what bed boundary is? Going from one type of rock to another type of rock. When you cross the boundary, especially if you have an inclination angle. If you have an inclination angle, you're crossing the boundary with an angle. In this case, you will see differences between the phase and the attenuation. But if you are actually logging a thick zone, same reservoir, same zone, no boundaries, they will agree. If you come closer to a boundary, they disagree. Okay, I don't want to go through the details of this because it requires also some electromagnetic background. Okay, but understand that if you're crossing a boundary, the two are different. Okay, if you're crossing a boundary, the two are different. If you are in the same formation, no boundaries, okay, then in this case they will be the same. Okay, so they be the same or different based on are you crossing boundaries or not. So when you cross boundaries, be careful for the induction tool. Okay. Unconventional resources development. Can source rock be clay? Please, again, as I said at the beginning, I'll say it again. Look at this. No and red. Please don't ever, never in your life think that clay will be a reservoir. Okay. You should not be graduating if you still think clay can be a reservoir. Clay is not, will not, cannot, will never be a reservoir. Can I be more clear than this? Okay. No, it will not. Right? Clay is never, will never be a hydrocarbon producing zone. Refrain from this question from now on. Okay. Don't ever think of it. Not because the unconventional reservoir has high gamma ray. It's clay. No, not everything that has high gamma ray is clay. The one that's clay has to have high thorium, high potassium. But I can have high gamma ray from uranium. It has nothing to do with the clay. Okay. All right. So source rock will contain, but you can actually have some clay components in the source rock, but the clay will not be a producing part. So the clay will actually lower the quality of your source rock, as if the same thing with the clay lowers the quality of our normal regular reservoir. If we have high clay component, that's bad news, huh? Because clay is never a source, it's never a producing zone. It's never producing zone, right? Okay. Unconventional evaluation. Why the unconventional reservoir has very low permeability? Okay. Why the reservoir has low permeability? I said it again. I will say it again one more time. What is unconventional reservoir? Unconventional reservoir are reservoirs, normal reservoir, but with very, very, very fine grains. Okay. So the property of the unconventional reservoir, it has very, 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 in this lecture, I'm stressing in some words, because guys, probably this is the last lecture we'll see each other. Be careful when you ask the questions. Clay, I would, again, don't ever think of the clay being a producing zone. Second thing, don't ever forget that the source rocks are very, 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 very fine grains. Very fine grains means the pore sizes are very, very, very small. Any small pore sizes will have very, 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 very low permeability. As simple as such. Okay, these are rules. We say limestone is a source rock if the grains are very, 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 very fine. Okay, so 0.004 millimeter will make the pore sizes very small, which makes the permeability very low. Okay. What is the basic difference between gamma ray and gamma ray tool? Okay, that's a good question, actually. I didn't touch that question before, but I will answer that question. Okay, one by one. What is the basic difference between, there is actually a gamma ray and gamma. What is a gamma? Gamma ray tool is a tool that uses the natural gamma ray activity from the rock. So the tool itself does not have a gamma ray source. Okay, so the gamma ray tool is a tool that does not have a gamma ray source at all. The gamma ray is coming from the formation. So the gamma ray that the gamma ray tool is reading is not coming from the source in the tool. Okay, it's coming from the formation itself. The formation will emit gamma rays in the clay zones for potassium, thorium, and also uranium. Then you actually acquire this. But the gamma tool means a tool that has a gamma ray source and detects gamma ray. Okay, so the difference is gamma ray tool does not have a gamma ray source. Okay, example is the gamma ray tool. The gamma tools, you have a gamma ray source. Example is the density tool. In the density tool, you have a gamma ray source, and you send the gamma ray into the formation, and you acquire the gamma ray back. That we call it gamma tool. It means you have a gamma source, and you count the gamma that comes out of the formation. Okay, after the interaction. Okay, so the two examples are, here is the gamma ray tool, doesn't have any source in here. It only has a detector. It actually gets the gamma ray from the formation. So there is no source in the tool. We call this gamma ray tool. The gamma means I have a gamma ray source that actually emits gamma ray, and the gamma ray comes back to my detector. So I have a gamma ray source and a gamma ray detector in the tool. So if you have your source mounted in the tool, that's a gamma. Okay, if you don't have a source, that's only a gamma ray. Okay, so that's the difference between gamma ray tool and a gamma tool. Okay. Related to lecture reservoir, use of the drilling mud. Oh yeah, this one is also a good one. But also we talked about this and covered it in the resistivity part of the characterization. Okay, said that we actually measure resistivity, but we know that the invasion takes place, and the resistivity can be affected by the mud. Okay, either you didn't understand the lecture, the previous one. Let me repeat it one more time. Here is our condition in any well. When we drill a well, there is mud in the well bore, and the mud, actually mud weight is higher in pressure than the formation. So that's why invasion takes place. Invasion means the mud will actually penetrate and go into my formation, okay, until a certain limit. Now we have 3 zones identified. One of them, we call it uninvaded zone. It means the mud did not reach there. So the uninvaded zone is a virgin zone. It contains the original reservoir structure from the fluids point of view. So the origin, because there is no invasion. Invasion did not go as deep as this. The other 2 zones either flushed completely or partially. If it's flushed completely, you call it flushed zone. If it is partially, you call it invaded zone. So we have a flushed zone, invaded zone, and uninvaded zone. When we measure our resistivity, we need to make sure that our resistivity is reading deep enough to look at the uninvaded zone. So in this case, you're looking at the virgin distribution of fluids. Okay, so that's why when we looked at this, the density, the resistivity, here is our resistivity tool. Here is our source and receiver. Here is our measurement. Here is the focus current. Our focus current will make sure that we see this zone and the deep zone. So when we calculate our fluid saturation, we use the deep measurement. What is the deep measurement? It's the measurement that reaches deeper into the formation, away from the invasion. Okay, so that's the resistivity that we use in our calculation. Now we can ask a question. If this is the case, why are you measuring 2 of them? If you only need the deep, why you're costing yourself other measurements? Why you are not concentrating on the deep? Actually, we use the 2 measurements in predicting what the permeability will look like. Okay, so the reason that we do multiple measurements, it gives us an indication of permeability. Okay, not because we need them for any fluid calculation. No, our fluids calculation uses only the deep measurement. Am I clear? When we use Archie or Siemens Doe or Waxman-Smith's Doe or water, whatever saturation model you're using, the resistivity you're using is the deep resistivity, not the shallow, not the medium. So why do you need the shallow and the medium? We actually understand how the rock permeability will look like. It's an indication of permeability, okay? So it's not an extra measurement for the sake of calculating fluid saturation. No, it's not, okay? All right. Can you please suggest some books or material on what? Yeah, okay. Guys, I always, when I teach this, I always give 2 references, okay? One of them I call it in-depth, and the other one is the basics. Some guys like to go in depth. For example, like when I want to discuss the photoelectric, okay? Not everybody knows what the photoelectric is because it requires a lot of physics. Some people like to get into details, okay? So these guys will have a book by name, Well Logging for Earth Scientists, by a very well-known guy. I was lucky to know this guy and work with him, Darwin Ellis. Darwin is a great guy. He's a very good physicist. He actually wrote this book, Well Logging for Earth Scientists. He actually looks at everything in details from A to Z. If you are a guy of details, so this is the book for you, Well Logging for Earth Scientists. If you are a guy for basics, you need to understand things because your background of physics is not that good, that strong. You may get confused and this kind of stuff. So the basic is another very good book, okay, by George Asquith or Dan Kirgowski, Basic Well Log Analysis. This is a good book, but it's basics. It doesn't go into details, but at least it will show you all what's required to understand the tools, understand the logs, and understand the interpretation. But to get into deeper into the tools, their design, the physics behind it, why I'm doing this, why I'm doing that, why I'm using this source, why I'm not using that source, what is the PE, what is the Compton. If you need to get into these type of things, then the Darwin Ellis book is the one for you. Okay. All right. Thank you very much, and I hope you guys got what you needed. And I really wish you good career from now on. Mayar, if
Thank
there's
you.
any other questions, yeah, go ahead. Sorry, go ahead.
Thank you so much, Dr. Mustafa, for this super informative webinar. Yes, we have like 7 questions only.
Okay.
How azimuth angle and inclination angle is found? I was very
Okay,
confused to solve it.
yeah, let me take that one. Actually, for the azimuth and inclination, guys, when we drill any well, we do what we call well planning. Because I am drilling from the surface, I need to reach a target. To go from the surface to the target, we do planning, well planning, okay? Knowing the geological column, knowing the previous experiences of drilling, I plan to place my well in a way to reach my target safer, to reach my target with no problems in drilling. We call this well planning. In well planning, you decide the trajectory of your well. Yeah. So you know the building angle, you know the azimuthal, and you know the inclination angle. So you decide on your inclination angle. And also you decide on your azimuth, which direction you're gonna go from the XY plane. So the XY plane is the azimuth angle. Your Z plane or the Z direction is your inclination angle. So I decide on my inclination angle and my azimuth angle before even drilling the well. Once I started to drill the well, the LWD company, the drilling company, they have tools to actually measure the azimuth and the inclination. So you actually get the well after the well is drilled. That's the company that drilled the well for you. It will give you a file. That file will show you every angle, azimuth, and inclination. So that file is a recorded file while the company is doing the measurement. So they have their own tools. They measure the inclination and the azimuth. Even if they have some old wells and these files are missed, we actually do what we call survey. Survey, we can actually use a certain type of measurement called surveying. We go there in the hole that's already drilled, and we can actually measure the inclination and the azimuth. So even if you didn't record it before, you can do it today. I can go with the surveys today and decide what is the inclination and the azimuth at every foot if I want to. Okay. So this all the inclination and the azimuth is known for every well ahead of drilling, during drilling, and after drilling if you want. Okay. So that's not a magic thing. That's not a secret. It's measured and planned for. Okay. All right. So knowing the azimuth and the inclination is known pre-drilling, during drilling, and after drilling. Okay, Lamaya. Sorry.
Thank you. And another question. Sir, as you said in reservoir characterization, the permeability only depends on pore throughout diameter, but Carmen shows the relationship between permeability and porosity.
Yeah, but you actually, yes, you're right, but you're not very honest in your question, because if you really go to Cosini and Carmen, you will see another parameter that you didn't mention. It's called tertiosity. Okay, you did not mention tertiosity. I don't know why. You measure porosity and permeability. There is another factor in this equation. Okay, be honest when you ask the question. There is a tertiosity. Tertiosity is the function of the pore throat. Okay, so that's the one that you missed in this equation. Okay, so Carmen Cosini they actually have the effect of the pore throat in the form of tortuosity. Okay, so it is there. It's not. Don't say it is not there. It is there, and it's embedded in the tortuosity. Go ahead.
Thank you, doctor. And another one, how can using barite affects PE reading? And is it available to run environment correction like we do in N/D tool?
Yeah, actually, that's a good question. Barite is a heavy weighting material. and barite has a very high photoelectric parameter. So that's why if you actually mix barite in your drilling fluid, your photoelectric will be highly affected. When? If you have a washout, okay? There are corrections for it. Yes, there are corrections for it. But I personally don't like the PE correction because PE is a shallow measurement by itself. It's a very shallow measurement. There is no room. Well, let me put it that way. I don't give a room for uncertainty for the PE. I don't like to work with PE with uncertainty. PE is a shallow measurement as is. Let's just keep the right things. PE is a shallow measurement. Now, if you put barite, which is very heavy, okay, in PE, it has very high PE factor, then any small barite will affect my PE. If the well is not in a good shape and I have washout and you have barite in the mud, please don't use the PE. Find a different way, right? And don't apply the PE correction. Yes, there are PE corrections. I know that. I never do it. I don't like it because as is, PE is a shallow measurement. Don't take a shallow measurement that's very heavily affected and apply correction. Corrections for what? It reads only 1 inch, for God's sakes. Then you're doing correction for 1 inch measurement. You know what the GIGO is? Garbage in, garbage out. That's as simple as such. Yeah. So don't do that. Don't use PE, guys, unless you're sure that your borehole is in a good shape. Right?
Thank you, Dr. Mustafa. And how does oil migrate from the source rock although it has no porosity and hydrocarbon is sealed between the layers?
I actually answered that question in the previous webinar. Actually, guys, and I give an example. How long does it take for a bubble of gas to go through a 10-meter thickness of rock? And we said it depends on the permeability. And we said if the permeability is in the order of nano, it will take 300 million years. And the Earth is 5 billion years. So we have actually reservoirs that from the Jurassic, reservoir from the all these long geological ages. Okay, so these geological ages are millions of years. So it actually, even if the permeability is very low, the probability of migration is there. And that's actually God-given, guys. If the permeability is high in these source rocks, we'll be in deep trouble now. Should have been gone long, long ago. Thank God it has very low permeability, because very low permeability means there is a keeper for our hydrocarbon, that God kept this hydrocarbon for us until we understand how to get it. Okay, so now we understood how to get it, and thanks God the permeability is very low, and it takes millions of years for this bubble of gas to go for 10 feet thick of source rock up to the migration of the reservoir. Okay, so yes, it's very low permeability, and that's why it takes a very long time, and that's why we have hydrocarbon till today in the source rock. And if the source rock does not have this very low permeability, we will be in deep trouble. Okay, so thank God for this, and go and pray rakatain wala haja.
Thank you, doctor. If is low
Resistivity.
resistivity in reservoir is good or bad?
Well, that's a very good question. Actually, there is something called okay. There are two reasons for low resistivity. Low resistivity can be low because of water. That's bad news. Okay, because water is conductive, and if there is water in our rock, resistivity will be low. So if I see low resistivity, sometimes it's bad news. But if you are careful enough, there are something called low resistivity pay. Like if you are here in Egypt, I know that so many people are from all over the place. If you have thin laminated reservoirs, it means you have layers of sand shale sequences. And these layers of sand shale sequences, if they are put actually together, they will affect your resistivity and make it read low. Okay, so even you have hydrocarbon in between the clay layers, the resistivity will read low. We call this low resistivity pay. The other thing is, if you have fine grains sandstone, like siltstone, for example, if you have siltstone, silt is very fine grains. Okay, very fine grains means it contains a lot of irreducible water because the capillarity is high. Fine grains means capillarity is high. If the capillarity is high, means it contains a huge amount of water, but this water is irreducible. Okay, irreducible means it's actually controlled by capillarity. It's not going to flow. It's not the water that flows. Okay, so the water that's irreducible will drive the resistivity to read low as well. So either reading low because of the lamina, or reading low because of the capillarity, or reading low because of the water. The only one that's bad is the one reading low because of the water. But the other two is not bad. But it needs experienced person to know if this low resistivity is because of the water mobile, or because of the water capillary, or because of the lamina. Then you can actually be a hero when you find out a zone that has 1 or 2 ohms, but still produce absolutely 100% hydrocarbon with no water whatsoever. We call this low resistivity pay. It's a pay, but it has low resistivity for one of these 2 reasons. Either it's fine grains like siltstone that actually contains high irreducible water, or it's laminated, that's the lamina actually affecting the resistivity and forcing to read low. Okay.
Thank you, doctor. And another question, do permeability depends on fluid saturation?
It does in a sense. It does in a sense, but it actually, well, when you say permeability, I also like us to differentiate. Are you talking about absolute perm or relative perm? Yes. If you are relative perm, it depends on saturation. If you are not talking about absolute perm, no, it does not. Absolute perm is a structure dependence. Relative perm is fluid dependence. So the relative perm, yeah, it depends on the water saturation that you have there, SW. But the absolute perm is not. Absolute perm is rock structure dependent, but the relative perm is fluid dependent plus the rock structure. Right? So it depends which permeability you're talking about. Right, that's it.
And another question, can we be able to get real-time data from well with advanced tools?
Say it again, Mara. I didn't understand the question.
Can we be able to get real-time data from well with advanced tools?
Yeah, that's actually real-time data. We call it RTO, real-time operation. That's an old technology now, but been in the industry for about what, 15 years now, 20 years. So yeah, real-time data. You get the data through satellite from the rig to your office. I mean that became an old technology, by the way. Yes, we do that.
Okay. I think we don't have another questions, doctor.
Perfect. Thank you, Maya. Thank you very much.
Thank you, Dr.
Right, guys,
Moustafa,
thank you so
again.
much. Thank you, Maya.
Thank you. Thank you so much. And now, to highlight, this session has been recorded and will be uploaded soon on BioPetro YouTube channel. So kindly make sure to subscribe on our YouTube channel. Wishing you a great day and bye.
Bye.